Hi, I'm Oliver Grasl from Transemptive Consulting, based in Berlin. Our mission is to help companies transform their business, and we use simulations to help companies manage the complexity of transformation. And in my presentation today, I will teach you how to build great stories around simulations using Mathematica. Okay, so good morning, everyone. My name is Oliver. I'm a management consultant, and we use Mathematica to build simulation models, management models. And today I'd like to show you our approach to doing that. Now, I guess most of you know why simulation models are important. Essentially, what we tell our customers is this, in complex situations, it's just too risky to experiment with your business. It's too risky to change your business model without thinking about it in advance. And so one good approach to dealing with that complexity is to build simulation models. Okay, so instead of experimenting in the real world, build a simulation model, experiment with new designs, with new policies. In the world of business simulations, come up with different approaches, and then realize the design using prototypes as a guidance. Now that's the simple story, but unfortunately, in reality, even if you build a great simulation model, between having great ideas and actually putting them into practice, there's a big gap. Okay, and so what we soon realized is that in order to get people to take action, you need to tell a good story. Okay, so in order for your simulation models to have an effect on your business, you need stakeholders to take action. And we find, trying to tell a good story around your simulation model is a good approach to do that. So the question is, which tools do you use to do that? Okay, and traditionally, and the way we approach that is we have a sort of iterative process. So first of all, and this is just a problem-solving process, so we try to understand the challenge. We build a prototype, we call it prototyping. We prototype the business, build a simulation model, design new policies, test the policies, and eventually come up with some future scenarios, and then the storytelling starts. Okay, and we try to build a story around that. Now, traditional tools, which tools do most companies use to tell stories? They use PowerPoint, right? They build PowerPoint presentations. And if they're sophisticated, they might be using something more powerful, like Adobe's Creative Suite. And I think they're great tools, and I use them a lot myself. Okay, but the problem is they're not very good, and especially for this iterative part at the end. But when you're building simulation models, I'm sure most of you have done that before. You build a model, you build a presentation, and then someone comes up with a new idea, new data. You have to change the model. You have to change every graph in the presentation, which takes ages. Okay, it just takes a long time. And so these traditional tools, even though they're great for visualization, they're not so good when it comes for handling data, graphs, and algorithms, for what I call iterative round-trip engineering, i.e. working both on the simulation model and the presentation at the same time. And they're not very good at providing an environment for experimentation. And I think half the fun of having a good simulation is playing with it, experimenting with it. Even for top management, it's a useful thing to do. Okay, so now we know, and obviously we all know what a good solution to that is. We can use Mathematica, right? Because Mathematica is a great tool for building stories, for building interactive presentations. But now the question is, how do you approach that? Okay, now I don't know, one of the tools we use to build business simulations is, I think it's a system dynamics modeling tool. System dynamics is actually now fairly old approach to building simulation models. And a good thing about it is it uses a visual representation. And we find even, we can even speak to people who don't have a sophisticated mathematical background using this visual representation. And a good thing about these tools are firstly, they use a fairly intuitive notation. I'll get into that in a minute. Okay, you may know it already, system dynamics. And the tool here is, I think, but there are a number of tools on the market one can use. So first of all, they use an intuitive graphical notation. Secondly, they show you the overall structure of the system so you don't get lost in equations. Okay, so even though to us mathematicians, and I'm a mathematician myself by training, all these things, we could just do that in equations. And I actually like equations, okay, so I'd actually be quite happy to do that. But a lot of people don't like equations. And most people who like mathematics know what happens if they show mathematics to people who don't like equations. Okay, so that's why visualization is sometimes good. Secondly, you can show the overall structure, and businesses are complex, and we sometimes have simulations with 300 or 400 equations, and that gets to be quite a lot of information you need to handle. Okay, and these tools are good at doing that. And thirdly, you can hide away the details, so you can focus on the stuff that is important at that instant. Okay, so what I'm trying to say is, well, Mathematica is great, but it's also good to have visual modeling environments. And I think Wolfram knows this. That's why you get a system modeler. We've also looked at system modeler for building system dynamics equation models, and you can do that. But I'm not so happy with the current implementation. So that's why we're at the moment still working with iThink. And we find iThink is a very easy to use tool, and it can also be used by people who are not very sophisticated when it comes to dealing with technical details. Okay, so how do we combine the two worlds? Now, what we've done, we've used the power, essentially, of Mathematica to create a little parser, a little converter. And what we do is we take the iThink tool, we build a model, and actually iThink uses let's call it a pseudo-standard. They're trying to standardize the language they're using. It's called XMILE. It's an XML-based format. And we've built a little converter that converts the XMILE model into a .m file. Model.m, I've called it in the graph. And we also have a little system dynamics package which gives us utility functions, and then we can run it in Mathematica. And the good thing about it is, because you also all may know from your experience that one of the problems with building simulation models and having these tools is deployment. How do I get people in the company to use my model if the only way I can run it is by running it in a tool that costs a lot of money, that may not be easily accessible, and so on. And often, we're management consultants, so it takes us, let's say, 2 or 3 months, perhaps at most, to build a simulation model. Many large companies, it takes them 6 months to get a tool deployed. Okay, so by that time, we've left the company, and they're still looking for the tool. Okay, so that's no way to go. So firstly, Mathematica is a fairly good way to go, but obviously we can also use things like Wolfram Player. But what we also do is we actually deploy them using a web browser, and our converter can actually handle multiple formats. So we can convert it to Mathematica, which is great for the prototyping process, for the iterative process, and if we want to polish it for final use, we can deploy it to the web. Okay, so that's the technology. But obviously, we're here today to look at a concrete example. So let's do that. And this is the simple model I'm going to demonstrate. Obviously, this is a very simple model, much more simple than the model the models we build for our clients. But the good thing about it is it's something that affects all of us. And so I want to also give you an interesting model to think about. So this is a model that explains how we get things done. Okay, so essentially, we've got open tasks. We want to get them completed and turn them into closed tasks, okay? And how quickly we do that depends on our completion rate, okay? And the completion rate will depend on our productivity, and the productivity, as many of you may know, depends on schedule pressure, okay? And I think most people may have that experience, at least in my case, that's the case. If you have a deadline and it's approaching, well, let's say if it's 4 weeks away, the first 3 weeks you do nothing and worry about it, and then you get started, right? And get the presentation finished just on time, okay? That's what schedule pressure does to us, yeah? And the worst thing that can happen is that someone extends your deadline, because what happens then? You go out and party and say, yay, the deadline's gone away, and then you wait again for another 2 weeks, and then you get the pressure back again, okay? And I think all of us have experienced that, and that's a simple model to show this. Okay. So the key idea behind the model is that the schedule pressure isn't constant, but, that my productivity isn't constant. With the schedule pressure is low, then my productivity is fairly low, and then the schedule pressure gets higher and higher, and eventually my productivity goes up, and it goes up beyond the 1 because I end up doing overtime, yeah, and not taking any breaks and all the stuff we all know, okay? So that's our simple model. Now, what does this look like in Mathematica? Well, first of all, okay, we have this parser that converts it into a .m file. Initially, we built the parser using Mathematica itself, which is fine. Meanwhile, we use a different technology simply because we wanted to use a parser generator because we're not interested in building sophisticated parsers, and there are quite a few cool parser generators out in the market. And so we use one of those. So first of all, I import my system dynamics package, and then I can import the model. In this case, it's a .m file. And we've created in our package, created a few abstract data types. In this case, the simulation has a data type simulation, okay, appropriately. Good. So the first thing we want to do, we want to take a look at our simulation. So this is what it looks. So this gives them a little bit of statistics. So it tells me something about what kind of stocks I have. That's system dynamics speak. We discern between stocks and flows. Shows me my flows, my completion rate, what we saw beforehand on the diagram, and it shows me the converters, which essentially these are the equations, okay, and which constants I have. So that just gives me a quick overview of the model. And before I go on, I'll just quickly show you what the model looks like in the modeling environment. So if I can get this across here. Hang on. Okay, so this is iThink tool. So this is what the model looks like in the modeling environment. And if I wanted to, I could look at the equations in the modeling environment, and that's what they look like in the modeling environment, okay? And so I can play around with the model in the modeling environment. What we've done, we've imported it in its entirety into Mathematica, so now we're independent of the tool. Okay, let's get Mathematica back. Good. Okay, so now we've got the model in Mathematica. So the first thing I can do, I can look at one of the equations, and one of the equations is open tasks. Okay, so I can say, look, give me the equation, and in this case, this is the representation of the model within Mathematica. System dynamics is very simple from the mathematical point of view. It's difference equations. So to calculate the number of open tasks at time t, I need to know the number of open tasks at time t minus my delta time, and then I just add in the number of tasks that come in through the completion rate. Okay, so mathematically, it's really, really simple. Okay, and so that's why in Mathematica we didn't have to do any clever tricks to actually evaluate the simulation, because Mathematica can do that anyway, right? That's what the tool's for. Okay, so now I can say, look, let's work out the open tasks at time 5, and it gives me back a value. I can look at the open tasks at time after 20 days, and I've got 80 tasks open, and so on. Okay, and if we go back to the model settings, which is important later on for the simulation, I'm assuming that we have 100 open tasks, and each task takes me a day to complete, and my deadline is 100 days away. Yeah, so if I work steadily, I should be finished after 100 days. Okay? And so then we can experiment a little, make a few changes to the deadline to see what happens. Okay. Now, one of the problems with these tools, with these visual modeling tools, is handling different scenarios. And so our main objective was to put in some scenario management capability. Okay, and obviously the easiest way to do that, and what is a scenario? A scenario is essentially a collection of parameters, of settings for the model constants. Okay, and so what we did is, and that's a natural thing to do in Mathematica, we used the options, Mathematica options format. Okay, so we have an evaluating function which lets me override the equations, and then I can set the options using the standard Mathematica tools. Okay. Then we can create a scenario manager, which again is an abstract data type called scenario manager. And then I can define a few scenarios. So let's define a scenario. We've got 100 days, 100 tasks, but let's put the deadline at 80 tasks and see what happens. Okay? And then we can have a scenario with 100 days, 100 tasks, and a deadline of 100. And then let's look at what happens if we put the deadline up to 120. Okay? And then we can evaluate the scenarios. And then we get a graph showing us the different results. Okay, and now given the simulation I showed you beforehand, without going into the details of the model, it's pretty obvious what's going to happen. If I have 100 days, I get finished bang on time. If my deadline is a bit shorter, I still manage to get almost finished on time as my productivity goes up. Okay, but if I have 120 days, normally I should be finished after 100 days because I've only got 100 tasks, but it takes me 120 days. Okay, and that's just given the setting we saw beforehand. And I think you probably will agree, that in this case, the simulation fits pretty well with our experience. And if someone gives you 5 weeks to do a presentation, you're going to take 5 weeks. Okay, no one gets finished a week sooner. Yeah. Okay, and that's what this model shows. Okay. Now, obviously, that's just sort of what have we done up till now? We've defined a few scenarios, and we've showed some graphs in Mathematica. It's nice, but we could have done that using PowerPoint as well. It would have been a hassle if someone had said, look, I want to know what happens with the deadline 140. We would have to change the graphs and everything, but it would have worked. Now let's look at making interactive scenarios. And that's really simple as well. So we just create a scenario. I've called it an interactive scenario, but it's just another scenario, which I've added to my scenario manager. And now, using the built-in features of Mathematica, I can start manipulating it. So in this case, and we've got something called a graphical input device. That's part of our system dynamics package. So now I've got the schedule pressure we saw beforehand, but in this case, now I can start manipulating it. Okay, and this is just using standard Mathematica features. Okay, but I can start playing around, and we can say, look, some people, they never get productive. Okay. That's probably the productivity curve of some large corporations. Oops. My mouse isn't hitting it well. So just change the curve a little so I can play around with it. Okay. Now, this is, looks neat initially, but if you've got 100 points to do that, it's a bit of a hassle. So what we've added is sort of something we call paste points. So you can paste the, user interface has disappeared. You can paste the points, let's say from Excel. Mathematica now has a new data set, so we could use the data set feature. Yeah? So we're just trying to use the features of Mathematica to make it as easy as possible. Okay, but you can see how easy it is to create one of these devices. Okay, so it's so when you're building the interactive presentation, it's a very fast process. Okay, now we can see how this will affect our deadline. Okay, so we can go to the next page. In this case, I've got I can play around with my deadline, and I can see, whatever I do, even if I put the deadline down, my productivity is so low, it's going to take me a long time to do it. Okay, and so that lets me play around with my model. Okay, so now what's the lesson? What's the lesson from the model? I think this is an important lesson. I don't know if you've heard of Parkinson's law before, but essentially it says the effort needed to do an amount of work always expands to fill the time available to do it. And I think it's something that's definitely worth knowing. And to be honest, from a management perspective, it means you better have close deadlines because people are going to use the time anyway you give them. And from a personal perspective, it means that obviously the time you lose initially, you're never going to find again. And so in the end, you're going to end up working very, very hard if you don't manage to get the productivity up as soon as possible. Okay. And this leads me to the end of my presentation. So what's the conclusion? Number one is to really make business simulations effective, you need to be able to tell a story that motivates people to take action. I think that's the key takeaway. And what we've learned, even for business applications, Mathematica is a wonderful storytelling tool that's very, very flexible and very, very fast. And in my opinion, even though there's a learning curve initially, the learning curve isn't as big as one imagines. And we can handle fairly complex models using a very limited set of Mathematica features. Nevertheless, you want to use visual modeling environments because they're useful for maintaining large and complex models. And so one easy thing to do is to try and get the best of both worlds. And in our case, we import the model into Mathematica and run it there. Okay. Thank you.